So in the second section, we're gonna learn how we can operate or do some logic operations. So at first, we simply define logical statements, or in this case, propositions, as something that we can assign a value of true or false to that. And here we're gonna do more about that. Like if it's just a single statement or single proposition, and it's just true or false, then there's nothing to learn or nothing to do at all. So let's see what else we can do with that. Yeah, I have this sentence, but maybe it should be a meme or an image. But suppose your dad say, "Oh, if you don't finish your dinner, you won't have cake." So that means if I finish dinner, I'm gonna have cake, right? So what happened is me finish dinner, also me didn't get cake. So again, this kind of like somewhat counterintuitive. In this case, the dad is not wrong. The dad, your dad, my dad, anyway, the dad. I said, if you don't finish your dinner, then you won't have cake. But he doesn't promise that if you finish your dinner, you will have cake. And this sentence or this statement is different from the other statement. Let me write it out then. If you finish your dinner, then you will have cake. These two statements sounds like they are the same. In fact, they are not. And if you finish your dinner, there's no guarantee whether you're gonna get or not. So yeah, in a sense, the dad isn't lying, but in another sense, he is tricky. He tricked you into doing something you didn't want to. And so yeah, you're gonna learn in a moment that this is statement in the form of if then. That's the word if. It's if then. And shortly after that, we're gonna learn that this is not the same as not if and not other way. In other words, these two sentences or these two statements are different. This doesn't imply that. But before I'm giving you some fancy notations in advance, but we're gonna see this, But let's start from the first one. So just like when you can, just like when you can operate on two numbers or two variables. Like you have x, you have y, you can add them together to produce a new number. You have a number. That's a number. That's another number, and you get the result as another number. Similarly, in logic, we have a position, and then you operate that. We'll see in a moment what that thing means with another proposition to get a new position. And this is what we're going to do next. But let's first notice that I use 3 lines instead of 2 lines. Because these two have slightly different meaning. This one means equal. Both of these values on both sides of the inequality of the equal sign are the same. They all mean 3. But in logic, we don't use equal sign because they are not the same. They just happen to have the same truth value. Like for instance, I can say, let's say I love math equals to I hate rain. If you see this on the board, you will say what? It's kind of nonsense, right? I love math doesn't mean or isn't the same. Doesn't have the same meaning as I hate rain. But in logic, like they are both true. This on the statement on the left, on the proposition on the left, and then another proposition on the right, they are the same. They have the same truth value, but they are not the same statements. As you can see. So that means we have to kind of invent or use slightly different symbols to convey the fact that they have the same truth value. not exactly the same statement. That's why we have another fancy line for that. We're gonna stick with that throughout the whole lecture. And again, just like when you can add things, just like when you can have variables for numbers, we have variables for propositions as well. And usually when you read textbook about this, they are not saying this P and Q are variables. They are propositions. That is either true or false. But I'm using them, I am comparing them to variables because first they can be anything. They can be true, they can be false. We don't know that yet. And second, they are everywhere. So we should treat them as having either value, true or false. And then a logic operation. This is the name of the topic of the title. If it turns one or two propositions into a new proposition, so you do things with number, and then they might have different truth value. Give you a different result. And it is sometimes called Boolean algebra. If you happen to know this in advance, you would notice that, oh, actually, like this is actually the way you do math when you only have 0 and 1. You can somewhat translate 0 and 1 into 0 times 1, 0. Those kind of things. But if you don't know that, then don't worry about it. Mentioning what this statement means. So it's kind of like algebra where you can combine things, do things, produce a new thing, a new thing, or a new proposition. So there are some standard logic operations which we go over here. For example, like this is a claim. I'm not a werewolf and you are a werewolf. So this kind of have two statements. In this case, two propositions. The first, I'm claiming that I myself is not a werewolf, but and also you must be a werewolf. And these two sentences are combined or connected by the word and by the proposition and. Again, you can see this is an English part and not a math part yet. But then again, it's you understand this statement, right? When I'm claiming two things and connect them with the word and claiming that the first sentence is true and also the second sentence is true. This is what I mean by that. These two must be true for this whole statement to be true. This is what I mean when you combine statement or when you operate with statement. You have the first statement with some truth value, you have a second statement with some truth value, you combine them by some operation and the result is something. And we can combine things with, we can combine sentences in various ways. These are the ways we usually have. And there are 6 here. But first there are more than 6. But if you study, I think, electricity or something, you're gonna have to study more. When you want to, when you have to connect things, I think it's called logic gate. Yeah, logic gate. When you connect branches or legs to produce a new branch, then you're gonna need to know more about more than that. And second is that what we usually have, we have these 3 main, at least 4 main operations. This one is here just in case. Sometimes you see that, sometimes you don't, but we don't use that much in math. And also this one is also kind of important, but important in math, not outside math. You will see in a moment why. So these are the 6 operations that we can combine statements together to produce a new statement. Oh, and by the way, I think I missed a word, but this is what we call a compound statement. Just like you have compound sentence and you combine two sentences together.
We have compound
How positions or compound statements. Let's see what they are and how we.
But
Let me. Oh yeah, let's go to that. Oh yeah, there's this famous quiz. Only 10% of the students can solve this classic puzzle. So that's a claim. I claim this sentence. Since it's a claim, it is a proposition, and it's either true or false. But you don't know yet whether what I'm saying or what I'm claiming is true. And so your job is to try to prove or disprove my statement. So I'm saying that if a card shows an even number on one face, then its opposite face is blue. If it shows an even number on one face, then the other face must be blue. And you see these four cards on the table. And by the way, this statement is about this four cards, it's not about any cards on earth. If you want to verify this statement, whether it's true or false, which cards do you need to flip? Need? You don't have to flip all. Of course, you can flip all and you can verify that in seconds. Right? But what if you can't flip all? But if you have to pay me like 1,000 bahts to flip a card, then you're not gonna spend 4,000, right? If you don't have to. Which card do you need to flip to verify to see whether what I'm saying is true or not? Let's start from the leftmost card. This is 5. Oh, and I'm missing some statement. The requirements that each card, Oh yeah, missing that each card has a number on one face and a color on the other. And a color on the other. On the opposite side. So you cannot have 5 on one side and 8 on the other side, for instance. So these two cards, since you see a number on one side, then you can say for sure that the other side must be a color. But you don't know which color it is. That's your task. That's what I mean. So let's start from this one. Do we need to flip a 5? Let's take a look at the statement. If it's even, then I'm claiming that the opposite must be blue. But this one is not an even number, right? Then that means what? It means that it doesn't matter which color the opposite side is. The opposite side can be any color. Because that card doesn't contradict with my statement. I'm only claiming things about even number. This odd number is irrelevant. But you don't have to. You don't need to flip that. If it's blue, then it's okay. If it's green, then it's still okay. If it's red, then it's still okay. No problem about that. But for the second card, I think we can kind of agree that, right? That you need to flip this card because you can think of it, right? If it's blue, it can be either blue or not blue. If it's blue, then that means my statement is still holding. Even I'm promising that it's if one is even, then the other is blue. But if it's blue, then we are happy. If it's not blue, then that means I'm lying. If it's not blue, then I'm lying. And so in this card is flip. Because there are two cases. If it's blue, then it's correct. If it's not blue, then it's correct. This was still simple, right? But then, that's why the 10% is here. It is a kind of spoiler to say that, people must get it wrong, so you might sometimes change your judgment based on this statement. Do you need to flip the blue face? It seems like at a glance Like, oh, since the statement is about blue card, then you also need to flip the blue face. But then let's think about it for a moment. What could happen? It could be even an even number or an odd number. If it's an even number, then that means I'm telling you the truth. Like, the statement is still holding. I'm claiming if it's even, the opposite is blue. And this card is even, and the opposite is blue. So that's still hold. What about what happens if it's odd? Like if it's odd and the other side is blue, then it is irrelevant to my statement. Let me put the question mark here. Because if it's still odd, it doesn't say anything about my statement. I'm only claiming facts about even number. So if it's odd and it's blue, then good for you. It doesn't contradict with my statement. It neither confirms or contradicts. So we gain no information if it's odd. And that means if you flip, then you can say either it's okay, it still agrees, or it doesn't say anything. And in other case, you kind of waste a flip. You don't need to flip that. It doesn't matter if it's even or odd. It doesn't say anything about my statement. Which means that the last one needs to be flipped. Again, if you take into account of what possibilities are, if it's even, then this is when it contradicts with my statement. If it's even, but the other side is green, then it'll be incorrect. But if it's odd, then we don't care about that odd. Yes, anyway. Okay, so you need to check these two cases. And if these two cases happen, then that means my statement is false. And in the end, in conclusion, you need to flip the even number and the green card, which is counterintuitive. Right? This is what it is. And then we will see in a moment that the reason why we need to flip this screw card is that the statement is in the form of P then Q. And you have to check P. But is this equivalent or it's the same thing as not P then not Q? In this case you need to check not Q. And Q is the second statement. Q is blue. So not Q would be not blue. And this is the reason why you should check the non-blue card. Because my statement, even though it's one statement, it also implies the other one. So that's the puzzle. You didn't know about unless you know you study math and it is enough number of times. So yeah, and then we're gonna learn how to make sure that we understand the question or statement or the problem correctly using the logical operation. So let's start from, now we're gonna do math. Let's start from the truth table. That's a typo. It should be truth table. So truth table is a table, of course. It's a table of truth, meaning that it provides a complete list of all possible combinations of propositions. It has everything you need. Just like you have, kind of like a multiplication table. If your numbers are below 12 or smaller, then you can find all the possible products of two. Similarly, we have a table. In this table, we have all possible combinations. In this case, the combinations mean pairs because there are only two operations, or there are only two statements to combine, to compare. But yeah, that's on the right, on the left. And if you know some counting techniques, we think is what is like the last lecture for this semester. You will see that there are two values for the first
then
which is for P,
and
and then there are two values for Q.
And
And then to find the combination, you need to multiply them. And so that's why we see 4 lines. And that's all the possible combinations of two truth values. True, false, false, true, and false, false. So this happens is true. But I don't have one, but yeah, sometimes you have one, you only have true and false.
It's gonna be a
Short table.
And
sometimes you are given 3 or more.
I think
I think this was kind of like a high school
exam,
exam, right?
Oh,
2 is too easy, so let's give you 4 or 3 to work with. What way they're gonna be true to the 2Q?
Or in this case,
It's X possible outcomes. Of X possible combinations. Yeah, let's use the word combinations. I use the word outcome because I just taught another class and I use the word outcome a lot.
Combinations.
And usually when you have 3 propositions or 3 statements, you have P, Q, and R because
there are 3
the consecutive
letters.
letters.
Oh
yeah, by the way, yeah, we use 3 because P, and we use the first letter for the word proposition.
That's why it's P. For
3 there are 2 Q. Each of them can have 2 possible truth values.
Three
Of them so it's 2 times 2 times 2. If you have 4, you're gonna get 2 times 2 to the 4th, which is 16 possible combinations. That's gonna be like a pretty big table. You're gonna need to put 16 rows. I hope you don't have to go that far. If you have 4, usually we use PQRS
because at least the next
letter. But for this class, I think 2 is enough. Or maybe at most 3. But for now, 2 would be of this form. We have P, we have Q, so this gives you 4 possible combinations. And since these are all the combinations, then we can write all the possible results under the operation. If you combine 2 propositions and they are both true, then the result would be
true or false.
if you have 2 propositions, the first one is true, the second one is false, then the result would be true or false. You can determine everything. And let's say it's gonna be like true, false, depending on what kind of operation you are using. So let's start from the first one. The first one is negation. I think this is the only one when you only have one proposition. This is the opposite. So this is kind of confusing because this symbol has 3 different wording. First we call it negation. Negate to flip something over. Then we have the opposite. This is the description of the negation. And then the way you read this symbol is you read it as not. So if it's the left one is P, you read this as not P. Oh, in a sense, we use 3 different words to explain the same concept of flipping the truth value. Negation, opposite, and not. But yeah, again, it's confusing at first, but once you stick with symbols, then maybe you don't need to know those words anymore. It means whatever we have, then we flip it to the other side. If your statement is true, then the not of that statement is false. If your statement is false, then the not of that statement is true. For example, one of the plus one is true. And yeah, it's true, right? Then if you put the word not in front of that statement, in this case, not equals, this means not equals. Not equals. Not equals is the same thing as. Not equals is the same thing as using this symbol here. So that's this sentence. And then it will be false.
Yeah, this is
This is a statement. This is P. Okay.
This
This is not P.
Then
Like P is true,
then
then not P is
false.
false.
Just flip.
Flip, just like you flip numbers from
positive
to negative.
And
If you know algebra, it is 1 minus P. If you know the Boolean algebra,
if
you get 0, 1 minus 0 is 1. If you get 1, 1 minus 1 is 0. So it's flipped.
That's the first
First one.
Then
Then we have the conjunction. This is a fancy word for and.
When you read
Read this symbol, you read it as an and. P and Q. And not P conjunct Q. That's not how we use. Like P and Q. Like this implies that both statements or both propositions need to be true. That's like when you say, I'm a werewolf and you know, I'm not a werewolf, you are the werewolf. I'm claiming that these two statements are the same at the same time. Oh, sorry, they are true at the same time. That means if they are true, then that means what I'm claiming is true. But if at least one of the statements fails, maybe the second one fails, or the first one fails, or both of them fails, then what I'm claiming is false. For instance, if P is 1 plus equals to 2, A is a wall, then P and Q.
If you unpack
That you say that okay, N 1 plus equals to 2, and it's a wall.
I'm claiming
These two at once. And this the truth value of this statement
can be
found from a table, or in this case you can use English
to
to interpret that. Oh, this two. This statement is true because each individual statement is true. This is what it means by T. Oh, I'm missing that.
It's realized.
And T is 2. Which looks like someone is crying.
Now you
can't unsee that.
Okay,
next one we have disjunction. Again, another fancy word that simply means or.
And then you read
This statement you read P or Q.
Like not
pork.
That's
not food.
P or Q.
When I'm claiming or, I mean that at least one of them is true.
Like
For instance, I want to eat meat or fish. It means I want
at least meat
or fish.
or
Or both. I'm happy to get both if you give me both.
But I want
That to be true.
And
since this, we only need one only to be true, then they are true. When at least one of them is true. Which is in these three cases. If they are both true, then I'm even more happy. Even happier, right?
They are both true. I get
Both
things
that I want. If it's the first one, yeah, I'm still happy because I want one of them. If it's the second one, yeah, I'm still happy with the second one.
But if
they both fail, if I miss them, then
I'm
gonna be
not
happy.
And
And again,
can think of
it looks like
someone is smiling.
that's how you use the word or. That's how you use the table for the word or. By comparing with the usage in English and
in logic.
next we have exclusive disjunction. This one, let me put a asterisk here. It should be an extra part.
Because
Sometimes you use that, sometimes you don't. Because even in English, like the word or is ambiguous. Most of the time, if we ask you, if you are on a flight,
and a flight
and
attendant
then ask you, do you want coffee or tea? Nobody in the right mind would answer both. That would be funny, right? Oh yeah, I want both. Can you please put them in the same cup? This kind of statement is actually giving you option of one or the other. That's one. I'm not saying I'm gonna get you both coffee and tea.
in the same cup.
So for this special distinction or this exclusive or, we need exactly one of them to be true. So you can see that it's true when exactly one of them is true. If they are both false, then it's false. I get neither coffee nor tea. I'm sad. If I get both tea and coffee in the same cup, I'm so sad because that's not what I want. Just FYI, you don't do that too much. And yeah, second to last. And this is the part that about the card that people usually are confused about. This is the if then. If then. If the former is true, then the latter is also true. Somebody is saying a statement about if and then that person is claiming the sequence of statements. So if you look at the first two, these two make sense. So if I'm claiming that if you have dinner, you're gonna have cake, and then you have cake, then you are happy. But if you dad say if you have cake, if you have dinner, then you're gonna have cake, and then you didn't get a cake, right? Then you are not happy. So these two are the natural part of this if then. But the not so natural, but still correct. That if the starting part, like the prior one, is false, then it doesn't matter what the outcome is. Then the statement is considered to be true. It's not true that it's true. It's true because it is just not false. Nothing contradicts that statement. If you go back to the example about cake, the dad claimed something about what would happen if you didn't have dinner. He's not saying anything about what happened if you have dinner. He says nothing about that. And so if you have dinner, then everything is fair game. Anything can happen. Whether it's true or false, whether you have cake or not, there's nothing wrong with that statement. Consider that to be true. And so that's the confusing one. And lastly, we have equivalence. You hear this a lot in math, but not in life because you don't actually use this in real life. If you combine or if you compare two statements with this equivalent, or in this if and only if symbol, the name of the symbol matches. And that means both statements have the same truth value. And this might be what the dad meant. Okay, these two statements are the same value. So if they are the same, then the result is the same. Yeah, I'm happy they're the same. Yeah, I'm happy they're the same. If they don't match, it's different from the other, then the result is false. For instance, you can say, if the dad instead say if you have cake, if and only if you have dinner, then this is what we thought the dad promised us. You use if and only if, then it would agree with what we imagine. If you have cake, then you if you have dinner, then you have cake. If you don't have dinner, then you don't have cake. But utterly false. So that's the sixth one, yeah, the last one that we use often. So these are just a single operation. If you combine them, get a new one. And if there are more than two propositions, oh yeah, this is where you use three. Then you can create more columns. Just like how you can deal with numbers. More cases, more numbers to deal with, then it just has one. But just make sure that you cover all possible combinations of all propositions. In this case, 2 to the n, and it's the number of propositions. You don't think you have
Oh yeah,
I don't have an example for that, so let me come up with one real quick.
So
So for instance, if I ask you to create a table for P, then Q, then P. Let's start from something
P
R, Q, and P.
So
Then this is when you combine more than one statements. Then what you do is you still
first
you count how many proportions are there.
There are
Three, but these two P are the same.
They have
Are the same value, so you actually have two. So that's just P and Q.
So we can start from that and doing the rest. So
we have P or Q. Just like when you do math, you start from things parentheses, so you can do P or Q first. This one you can just look up at the table. If you combine two statements with the OR,
I'm claiming
that at least one of them is true.
That's true.
One of them is true. One of them is true. They are both false, so it's false. But it is what we have up there. And then we have to do that one more time with P. So now what we do is we compare what we want to compare this column, which is the third column, to the first column. Compare the third column to the first column. Or maybe let me use pink. By that is first, like for the first row, you compare this with that. Let me change it a little bit to P and P minus Q. So the order is the same. P and P or Q. What we do is we compare, we operate these two propositions. So it's T for P and P for P or Q. This is from the third column. Just like how you add or do things with number. And then you have to go back to, not go back, but maybe you have one next to you. The table for AND operation. So what is T and T? If you have two operations and you combine them with AND they are both true, that means the result is also true. This will correspond to the first row. Let's just put it there.
P and Q would be false. And
this would correspond to the first row when we have T and T. That's true. Then for the second one, notice we have 3 and then T. So actually, if P is true and Q is false, we still have T and T.
True and true. And of
course, that's the same as what we have above, which is true.
And next
we have false. Oh, sorry, the last one to be false.
That's why
it looks weird to me.
It's false. I mean, that's T.
And so what we have here is P, F, and T. Gives you 2.
And F
and T corresponds to the third row. This is where the left one is false, the
right one is true.
And lastly, we have false here
and
false there.
And so
the final column
is
when P is false and this P or Q is false.
So the result
is false.
And
that corresponds to the last row
of P and Q. And
so this one, this is what we need. This is the logical operation, the combined logical operation of P and P or Q. If they are both true, then the result is. If P is true, Q is false, then the result is. If P is false, Q is true, then the result is 2. And lastly, if P is false, Q is false, the result is false. This is what we have.
So maybe let's
Yeah,
give
another short example.
So
Let's see what if we are looking for
P,
then
then
Q,
then
Q.
And then my sales.
Yes, let's do the other one, which is if another if Q. So there are two operations.
We start
Start from listing all the
possible
possible combinations.
There
There are three propositions, but we have repeating Qs. So
There
there are actually two, so P and Q.
Then
Then we start from doing P then Q.
So we go
To the
table
table above,
like
P then Q.
Like
It makes sense for the first two.
Like if
The result, if they are both true, is true. If the first is true, the result is false, then it's false. But the rest are true.
It
It
doesn't
doesn't say anything about those cases. There's only one case when P and Q is false, which is when P is false and Q is sorry, P is true and Q is false. If I promise something, but I break that promise,
That's
the only case when it's false. So we get the first one. And then we have to combine that with if and only if Q. And so what we do is we compare the second column,
which we're gonna write there.
the third column to the second column, which is for Q. So for P then Q, for the first row, we are operating P then Q and Q. P then Q is true in the first row, and Q is true in the first row as well. So the result is true. My head is almost in the way.
And
Next, if P then Q is false,
and Q
is false, like this is
the result
for the second column, the result is true as well. Then we have what? The third row, P then Q is false, Q is true.
So we are
Doing true. If true,
yes, again. Because
they are the same.
And
And lastly,
if
P then Q is true, but Q is false,
so
the result is false. Oh,
my bad. That should be this one. Oh, fuck you.
and so this is the result
that
we want. This is the logical. This is the truth table for this compound statement. It's true, false. If P is true, Q is true, then this statement is true. If P is true, Q is false, then this statement is true. If P is false, Q is true, then this statement is true. And if they are both false, then the statement is false. And so that's how you create a new
table from
values of order operations. So that's the end of the second section.
And yeah,
as usual, there is an exercise for you to do.
Okay.